Isn't this exciting? Find the measurements at right for this polygon. So there's some polygon here that's displayed on a Cartesian coordinate plane, so we can get a sense of some of the lengths looking at units here. We were asked to find the perimeter, the area, and we're also asked to find the distance between distance from point C to point F, from C to F. Or so let's begin. I guess probably the easiest thing to do would be to go through and kind of mark up some of these lengths. So I'll just write some lengths in red. So as I travel from D to C, I go a distance of 1, 2, 3, 4, 5 units, right? And if I was to go down and look at this below, this line at D ends up hitting the value 10, and the one for C ends up hitting the value 5. And I can take, the 10 minus 5, and I get a length of 5. So I could do that for all these, but I can just count because it's very straightforward here. 1, 2, 3, 4, 5. So this is 5 units long also. Um, this is 2 units long. I'm going to save the ones that are not vertical or horizontal for later. Down here I've got 1, 2, 3, 4, 5. So a lot of these sides are 5 units long. 1, 2, 3, 4 units long. And then I have a couple more diagonals. So I guess let's take a look at this particular diagonal first. It's from A to B, or from B to A. So I'm going to sketch this right triangle, and I can see that the distance from point A to point B, just isolated along the vertical change, is 3 units, and the horizontal change is 1, 2, 3, 4 units. And this is actually a Pythagorean triple. I've got this one fairly well memorized, right? When the legs are 3 and 4, the hypotenuse is going to be 5. If you don't remember that, you can always just take the legs, square it, take the other leg, square it. You get 9 plus 16, and when we add those together, it's 25. And of course, this is equal to the distance squared. I guess I'll just call it d, distance squared. So d itself would be the square root of that sum, and d would have to be the square root of 25. So the length from A to B is 25. Unfortunately, the other 2 diagonals don't look like they're Pythagorean triples, so let's look at them. I've got this one just along here, which is 1, 2, 3, 4 units long, and then along here is 2 units long. Down here, this one is 4 units long. So this is nice because this is the same, right? If I find the length of DE, it's going to be the same as the length of FE, and that's because they both have legs of 2 and 4. So using the Pythagorean theorem, we can get that. Also, these are right angles. They're meeting, one's horizontal and one's perpendicular. And if you think about it, these would have to be the same because of side angle side. You can see the 4, the 2, and the 4, the right angle, and then the 2, the 4, the right angle, and the 2. So by side angle side, they're congruent also. So I'm just going to find DE, and it's going to be the same for EF. So what I'm looking at here is 4 squared plus 2 squared, and that's the length of that distance DE. And I could write it like this as well. This is what I want when I want to talk about segment DE. And if I want to talk about the length of the segment, I've just got just the DE. So this notation indicates I'm talking about the length of segment DE, and the length of segment DE is going to be the square root of 4 squared plus 2 squared. So this is 16 plus 4, which is 20. So what we're looking at here is the square root of 20, and I can convert that to a decimal. If I look at root 20, it's approximately 4.47. Now, there's a disadvantage here. This is a decimal approximation, and there's a lot more decimal values to root 20. And depending on the purpose of this problem, or the purpose of, I could be constructing something where precision matters a great deal. So it's probably preferred to use the exact answer here. So root 20 is the exact answer, and I could write this exact answer in a simplified form. If I look at root 20, that is 4 times 5, and I was basically breaking it up because I know this 4 is a perfect square. I can rewrite this as the square root of 4 times the square root of 5, and root 4 is the number 2. So what I have here is 2 root 5. So this is the simplified radical version of the length of DE. DE is 2 root 5. So, and by the way, that is also the same length as EF. So I'm going to go ahead and erase that. You can rewind that if you need to take a look at it again. But this here is the length of that particular side. And let me just, can I drag it up here? There we go. So if I want to talk about the perimeter now, I think I can do this. Let me go through and get all the fives. I've got 1, 2, 3, 4 fives. So I'm just going to write this down as 4 times 5 plus I have a 2 and a 4, so I'll just write that down as plus a 6. Then plus, and then I have 2 of these things, right? This is a 2 root 5, and this is another 2 root 5. So I can multiply that, and I can say, look, I've got 2 of the 2 root 5s. Whoops, let me write that. 2 times 2 root 5. So I could simplify this if I think I'm missing a part, aren't I? 5, 10, 15, 20, 24, 25, 26. So 5, 10, 15, 20. Yeah, I am missing a part. I'm missing right here. That's very embarrassing. So 5, 10, 15, 20, 24, 25, 26, 27, 28. So this should be 28 when I add them. And this, if I'm going to combine those two, should be the number 8. So what I have here is 20 plus 8, or 28, and then plus 2, or actually I can rewrite this as 2 times 2 is 4, so I can write this as 4 times the square root of 5. Now that's my exact answer, and I can bring that around and write that as a decimal approximation. So let me turn on the calculator and go 28 plus 4 times the square root of the number 5. So there we go. So I've got 28 plus 4 root 5, and when I press enter, I'm getting that this should be about 36.9. So about 36.9. And again, there's no indication of what these units are, but I will put that it's units, right? 36.9 units is the length of the perimeter. That's the approximation, and this is the exact answer. Both of them are units. So let's talk about the area of this. I think I'll switch to the color green, and I think this will work for us. What I like to do is consider this large rectangle. So I'm just kind of sketching a rectangle around it that will hit all the vertices. And my strategy here is if I could figure out the length of, or the area of that rectangle, and then subtract a few pieces from it, I could figure out the area of the polygon that I started with. So the dimensions of this are what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11 units long from here to here. And this is starting at 15 and going down to the number 5. Well, from 5 to 15 is a change of 10 units, so this is 10 units long. So I know that the area of everything there is 10 times 15. 10 times 11. It's 11. So I've got 10 times 11. So that's 110, but I need to subtract some stuff from that. So let's figure out what we need to subtract. Probably a simple thing to subtract would be right here, this little rectangle below. And if I look at the dimensions of this rectangle, it's 2 by 1, 2, 3, 4, 5, 6. So 2 times 6 is 12, so I need to subtract this 12 units. I can just go ahead and come over here and I'll write minus 12. And let's see what else I can subtract. I need to subtract, I think this would be an easier thing to look at as this rectangle. So this rectangle has dimensions that are 1, 2, 3, 4 by 1, 2, 3, 4, 5. So this has an area of 20 square units. So I'm going to subtract the 20. And then it looks like I've got several triangles here. This one triangle it has a dimension of what, 1, 2, 3, 4 by 1, 2, 3. So 3 times 4 is 12, and this is exactly half of that area. So this has an area of 6 units, 6 square units. And these two triangles, actually, if I was to put them together, they would make a rectangle. So I could do it that way. I could say, in fact, if I look at it, the area that I need to take away, if I was to take this top one and rotate it down, I think it would land right into this space right here. So this might, you can look at these separately if this is a little overly confusing. But what I'm saying is, hey, if I subtract the area of this rectangle, it would be equivalent to this triangle up above and this triangle down below. And the dimensions of that are 2 by 1, 2, 3, 4. So that's 8 units, 8 square units that I need to take away as well. So no sense in taxing myself with arithmetic. So let's see here. 10 times, 10 times 11. Now, I think arithmetic's looking easier compared to how I'm using my calculator. I need to subtract 12 and oh, what the heck, I'll throw those together and subtract 26. Did you see that? I added 20 and 6. And let me subtract 8 also. So when I do this, I get an area of 64. This is 64. And these are not units. These are units squared, right? This is an area. And that was a nice, clean number, right? Perfect area, no radicals in it, no fractions, just 64 units. All right, the final question that we have here is, what's the distance from C to F? Is that what it said? Distance from C to F. And for that, I think I'll switch to this beautiful blue color. I hope this isn't too busy, but here's where F lives, and up here is C. And I'm trying to find this distance from C to F, and it needs to be a straight distance. I'm kind of drawing a curve here. And to do that, I'm going to investigate using, I guess I'll do this right triangle. So along the top and then down this side. So if I could figure out the dimensions of that right triangle, right, I could use that to build the length of CF. So across the top here, I have a length of 1, 2, 3, 4, and 5. That's nice. And then going up and down, I think this bottom is at 7. And up here is at 15. So if I take the 7 and subtract 15, that should give me 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is 8 units long. So I'm basically trying to figure out this distance, this hypotenuse, for a right triangle with legs of 5 and 8. So that's pretty straightforward. I'm just going to come over here. I'll just say this distance. Actually, I'll write it like this. The length of segment CF is equal to the square root of, one of the legs was 8. I'll square that. And the other leg was 5. I'll square that. Let me double check. Yes, 8 and 5. This 8 squared is 64. 5 squared is 25. If I combine those, I get 89. So what I'm looking at here is that the length of CF is the square root of 89. And I think that can't be, I think that exact answer can't be simplified. I don't think there's any perfect squares in 89. So I'm going to write this as an approximation also. These are units. And as an approximation, this would be, I have no idea what the square root of 89 is. Second square root 89. It's about 9 point, square root of 89, about 9.4. Okay, so I'm going to write about 9.4 units. All right, that's a rather involved problem, but we were able to find the perimeter, the area, and the length of 2 points that it's not, I guess it's a diagonal. It's joining 2 different vertices from across the shape. So I think it's time to move on to 7.